Ryan is a core contributor to Elm, the Elm programming language.
It's true.
Am I making? I'm not exaggerating.
I think 2 lines of code.
So the Scala meetup, they thought they had something special going tonight, but we have a core contributor. So thank you, Ryan.
Thank you. So thank you. As Chad said, I'm Ryan Levick, and my Twitter handle is Itchy Ankles.
Hi, Ryan.
Today I will be talking about Elm. Who here has heard of Elm before? Oh wow. Okay, good. Thank you. So I'll be getting, for those unfamiliar, I'll be getting into what is Elm. But before we talk about Elm, I'd like to talk about the problem that is JavaScript. Oh. The problems with JavaScript. So who here writes JavaScript on a daily basis? So like lately, that's been me as well. So despite some nice things that people have done with JavaScript and some funny quirks that we've all grown to love, JavaScript does have certain problems with it. It's verbose. It's inconsistent. It's imperative. If you're a non-functional programmer, then you probably think that's not a problem at all, but you're wrong. And most of all, it's not type safe, which leads to all kinds of bugs that a computer could help us just avoid in the first place. So the unfortunate situation, though, is that we have to use browsers, and we want to build things in the browser, and that means we have to use JavaScript. There's no other way, and that's probably not going to change, probably ever, or at least in the foreseeable future. So people have come up with lots of different ways of getting around this. Who here has used an alternative to JavaScript, like ClojureScript or TypeScript? Because we can only use JavaScript in the browser, a lot of people have come up with ways of not doing that, and we have things that compile down to JavaScript instead. And that's where Elm comes in. So what is Elm? Elm is simply a language that compiles to JavaScript, so you can run it in the browser. And everything that you can do with JavaScript, in theory, though still not yet in practice since it's quite young, you can do in Elm as well. Elm also embodies the idea of FRP, functional reactive programming, that we heard about in the last talk. And we'll start to see a bit more of what FRP brings us and what it means to program in that style. Elm is quite similar to Haskell. So we saw a bunch of code examples before with Haskell. Elm is sort of like Haskell Lite. If you've ever been really intimidated by Haskell before, I would recommend taking a look at Elm because it sort of doesn't dive as deep into some concepts that Haskell does. Makes it less powerful, but at the same time, much more approachable. That was sort of the whirlwind introduction, and the rest of the time, we're kind of going to be going through code examples and stuff like that. So I'm going to come back here and use my computer. So the first thing we're going to take a look at is, I can't see, there's a pole in the mud. All right. It's all right, I've memorized this. So anyway, here we have, I'm running this thing called Elm Reactor, and I run it in a certain directory that has a bunch of Elm files in it, and each one of these is sort of standalone. I didn't do a whole project, although you can find one where I implemented Flappy Bird on my GitHub, and I'll tweet that out later, which is a full project, but each one of these files sort of represents a step in our understanding of Elm. So we're going to take a look, wrong one. We're going to take a look at some code here, and you can see these are just the files that were present in the browser screen there. So since this is sort of an interactive, is this big enough, by the way? Should I probably, is that good? Yeah. Since this is an interactive tutorial here, I think it's probably best if you have a question, just go ahead and shout it out, and we'll sort of answer them as we go. And of course, if you want to wait till the end, you can do that as well. So the first thing that we see when we open up an Elm file is at the very, very top, we have something called main. And for those of you who have programmed in Haskell, also Java, things like that, you have a main function, and this is sort of where runtime hooks into your code and runs it, starting from main. And this top line right here that I'm highlighting is the type signature of main. So it basically declares there is going to be a function called main, and it is of type element. So we have no inputs to this function, we just get back a type element. Now main in Elm is always of type element or signal of element, and we'll get to signals in a little while. So you should be thinking, oh, I remember signals from the last talk as well. So we have sort of the same ideas from the last talk. And then down here, we implement the main function on line 2, and basically we just call a function called plain text. And plain text, as you can see from this comment right here, plain text is a function that goes from string to elements. So we pass in a string and we get back an element. And the way you can think about elements are like things in the browser view. Now what this compiles down to in actual JavaScript, CSS, and HTML is sort of, honestly, I don't even know, and sort of not even important. It's quite interesting when you're programming with Elm because you don't really ever know what you're working with. Am I working with a canvas? Am I working with just DOM elements? That's sort of abstracted away from you, and you really don't have to think about the browser like you traditionally do with JavaScript. When I'm programming with Elm, I never open the console, the JavaScript console, or the DOM inspector or anything like that, because there's just no need to do it. At least so far. Who knows when things get more complicated. So let's see what this looks like when we actually run it. And so here it is, whoop-de-doo, not very fancy, but here's Hello World in Elm. Are there any questions about Hello World so far?
What's the HTML and CSS?
Yeah, sure. This will be a first for me as well. So it looks like we've got our normal head and body. We've got some script because the Elm runtime has to be in there. So if you're worried about like, I really can't send much, I gotta worry about like getting my JavaScript to the browser. The whole runtime obviously has to come with this, so you keep that in mind. And then here's some sort of inline scripting here where they just put in all this stuff. And I guess this is where the magic happens, right in here. Anyone can see. So what this all means, you can sort of go into, Elm is on GitHub, by the way, if you want to check out how they go. Elm is written in Haskell and compiles to JavaScript, so if you're familiar with Haskell, you'll definitely be able to get in. And if you're familiar with JavaScript, a lot of it is written in JavaScript as well, so you can kind of tackle it from either side. All right, does anybody want to see anything else in here for the JavaScript nerds in the room? All right, cool. So we have Hello World there. The next thing we're going to be talking about in step 2 here is about how to place things inside the browser. So here we see a bit more code. Don't let this freak you out. It's 8 lines long, I know it's a lot, but we're going to go line by line. So we have our main function again, just like we saw, same thing, it's going to be of type element. So whatever we call, at the end of the day, it has to return an element, and that's what Elm will kind of run with from there. And we have 2 functions here, one called place, that is, goes from element to element, and one called toElement that takes a string and turns it into an element, basically. So again, like I said before, Elm is sort of just like Haskell. It's completely purely functional, referentially transparent. If you don't know what that means, we can talk about that later. But one difference with Elm, though, is that it is strictly evaluated. So arguments to functions come in like basically evaluated already, whereas in Haskell, they sort of wait until the very last second to do that. And as was mentioned in the last talk, that's actually sort of a good thing when it comes to game development, because in game development, you want strict evaluation. So first, let's look at this toElement function here. Again, it goes from a string to an element, and basically we call this provided function centered and toText on the string. So string gets passed to toText, it turns the string into a text, something of type text, and then center takes that thing of type text and turns it into an element, presumably as the function name indicates centered within that element. And once we have that element, then we're going to place it inside of a container. So you can see this function here, container. It takes two integers right here, which are sort of the size of the height and the width of the container, and then it takes something of type position. So that could be middle, upper right. You can sort of create your own positions and things like that. But there's a provided middle function that returns a position that is in the middle of the container, and then we pass that element into the container, and it sort of centers it in the middle of this 500 by 500 container. And then we kind of all put this all together. We first turn the string hello world into the element, and then we place that element inside of our container, and place, again, returns an element, so we're all happy. So does everybody see how the types kind of flow from one to another? We go string to element to element, we end up with an element, and that's what Elm needs to sort of run itself. Are there any questions about the code so far? Anything not 100% crystal clear? Cool. So let's see what that looks like then. We can see, this is sort of weird because my window's too big, but it is, there's a 500 pixel, let's see what for Raymond over here, what this looks like. Yeah, I guess we've got like a div here, and yeah, here's our sort of inner element in here. Here's our 500 by 500 element right here as a div, and it's sort of placed in the middle of it. So that's sort of placement on the screen. Does anybody have any questions at all? Great. So if for any Haskellers in the room, you may be noticing that I've used things like parentheses, which in Haskell, normally you don't use parentheses, you use things like function composition to get things done. Things like the period sign in Haskell, compose functions together, you have the dollar sign in Haskell as well. So if we look at this fancy placement here, so fancy placement is the exact same thing as we saw before. And let me go ahead and sort of, I remember how to split my screen here. Let me just do this. Sorry.
Can you make that bigger?
Yes, definitely. So on the right side here, we have our previous incantation of what we see on the left side here. They're functionally exactly the same. The only difference is we have certain little symbols here that are themselves functions, that take functions and other functions and sort of compose them together or place them together in certain ways. So has anybody used F# or Elixir in the room before? Cool, so if you know Elixir or F#, then you'll be familiar with this. This is the pipe operator, and basically sort of pipes this hello world here into toElement, which is then piped into place. So you can think of it as Unix pipes for those not familiar with F# or Elixir. You're taking one, pushing it into a function, then pushing the result into another function. And again, this is totally synonymous with what we have right here. So if you have sort of like these kind of cones that go down, and you're sort of calling a function, then you're passing that as an argument to another function, passing it as an argument to another, so on and so forth. It's probably more readable if you do it this way. Let's expand this out. So our place function doesn't really change at all, but then we have something like this here. This is function composition, and this is function application. So if you're a Haskeller, this would be like this. But if you're not a Haskeller, that probably means nothing to you.
Would you write that point free?
So in theory, you could write it point free, except that Elm does not currently support that. So like there is a way, in Haskell I would just write it like this, right?
Yeah, exactly.
But you cannot do that in Elm as of right now. But there are definitely, so Elm, another great thing about Elm is that it's sort of really nice for those who have never done purely functional programming before. There's always huge discussion on the Elm, mailing list and the Google group and stuff like that about should we introduce this concept. And then the creator of Elm, Evan, do you remember how to pronounce his last name? Crazy last name. Is really great about deciding that yes, we could do that, but maybe we should hold off. Like, will it really make our code more expressive? Arguably so. Function composition and point free style are awesome, but it's really confusing if you've never encountered it for the first time. So it's sort of a design decision to keep things simple. And in a way, you can see that arguably these function application and function composition operator or functions here are sort of maybe more readable than they are in Haskell. $sign doesn't really tell you anything about the direction of where you're applying your function, but this sort of backward arrow does tell you I'm applying this argument to the right backwards to the function on the left. And same with the pipe operator, or the pipe function, excuse me, and main up here, it's sort of indicating the direction that things are flying. So arguably, you have sort of more expressive or more clear function composition.
Question, can you leave off the last pipe operator in the last line? Does it need the last line?
The last line here. Yes, it does, because otherwise it would be combining the function to text.
Yes.
So I think it's the same in Haskell, if I'm not mistaken. If you did period here for function composition, and then didn't do a $sign here, it would not compose the functions correctly, if I'm not mistaken. But yes, so again, just to prove to you that this is the same thing, we'll go to fancy placement, it does the same thing, and ends up being, for the JavaScript nerds in the room, ends up being exactly the same thing that we saw before. So they're effectively the same, and you can sort of go ahead and at your leisure learn concepts like function composition, function application, and sort of use them when you start to feel more comfortable with the concepts, which is really great.
One question.
Yeah.
How does the pipe function work when you have more than one parameter?
I believe then you would, so like let's say place took 2 parameters here, then basically it replaces, if I'm correct, it replaces the first argument in that. So if the second argument replaces a string, for instance, like you would write it like this, like a nice string here. And then of course you'd have to change place down here as well, but this is sort of how it is. And this is how
works the same in R. R has this concept.
Cool. Yeah, and it's the same in Elixir, and I believe also the same in Sharp as well. So there we go. Any more questions about placement, fancy placement using function composition or function application? If you don't understand function composition and function application, there's some really awesome resources on the internet for learning these things, and I'd love to talk to you about this afterwards as well. But unfortunately, I have to move on. So let's go ahead and just close this. The next thing I'm going to be talking about is input. How do we handle the user input? And this is sort of where things get really funky. The reason for that being is that we're going to have to talk about signals. Now, luckily, we already had a talk where signals were mentioned, and we mentioned the signal graph, where we create these graphs of signals and sort of work over. But it's kind of fuzzy, and it took me a while to understand what the signal was. Now, if you're not familiar with Haskell or purely functional programming, close your ears for just a second. For those that are, signals are just monads. Ooh, the monad word. Yeah. So, but if you aren't familiar with those concepts, then the way you can think of signals as being is just something that when something happens, like let's say a mouse moves position, or we click the mouse, or we tap the keyboard or something, it will emit a value out. And you can sort of, my code is just going to re-evaluate itself given these pulsing values. So as these values come in, just all the code will be rerun. This is sort of the way you can think about it, and the nice thing about that is it's pretty easy to reason about. Okay, I just have to, every time a new input comes in, I just kind of follow the thing all the way through again. There's no state to think about or anything like that. Everything just happens, and then we throw that all away and do it again. That's really nice. It's obviously, that really happened, extremely inefficient, but luckily the runtime takes care of that for us, and so we can think in one way, have the runtime do it another way, and we kind of get the best of both worlds: efficiency and ease of reasoning, where we can just think of things as pure functions from one input to an output, and have the runtime take care of itself for us. So I said earlier, main must either be an element or a signal of elements, and so here we're taking advantage of that fact. We're now going to be using a signal of elements as our signature for main. And let's skip the implementation of main just for a second and talk about render position. So what render position will do is it's going to take an input of a tuple of ints and return an element. And the way you can think of this, maybe a better position would have been like render mouse position, because that's exactly what we're going to be doing. And here in the implementation of that, you can see that we get a tuple of ints, one of them representing the position of the mouse at x, the x coordinate, and one representing the position of the mouse at the y coordinate. And this underscore here simply says, I don't care about the y, I don't care about the second thing. Just give me x, whatever it is. So we're throwing away y, we don't care about y, and we're going to show takes an int and turns it into a string. Then if we remember plain text takes a string, turns it into an element. So now we have an element here representing the position of our mouse at position y, which is really great. Exactly what we want. And then, but the thing is, this function here takes a tuple of int and int. Now, mouse position up here, which obviously represents the position of the mouse, is of type. So let's just write this out. Mouse dot position, and I should never type in front of people. It's the worst. Mouse dot position is a signal of int of int. So we can't call render position just with mouse position because the types don't line up. We want to be able to pass in a tuple of int and int, not a signal of tuple of int and int. So we have to somehow take out the tuple of int and int away from the signal and run it through our render position function. And the way we do that is something in Elm called lift here. So I'm going to move this back up here. And for those familiar with functional programming, lift is essentially map. It maps one signal to another given some function from A to B, take a signal of A and it returns a B. So we can sort of lift up our render. The reason it's called lift is it lifts up render position into the signal, and we can now run our tuple of int to int into this render position. Does anybody have any questions? I know this, if you've never seen stuff like this might be slightly confusing, so we can go over it once more if anybody's feeling uncomfortable. No one? Come on. You guys are smarter than me, I didn't get this stuff. So once again, just to really hammer this home, we have render position, and it does not work with signals of tuples of int and int. It only works with a tuple of int to int. So we have to lift up that render position into the signal so we can pass a signal of int to int and sort of run the inside, like we unbox the signal, get back the int event, and pass it through render position. So we can take a look at what that looks like inside the browser here. We have input here, and you can see as I move the mouse around, everybody can see that, as I move the mouse around, it's printing to the screen the x position of that mouse. So if I try and move in the same x position as I move down, it doesn't really change. If I move back and forth like this, it's changing all the time. So it's sufficient proof that this program maybe sort of works. Are there any questions about this? Maybe JavaScript nerds are really excited about how this works.
So Ryan, a signal is basically like a burrito, right?
Yes, signals are like that. And if you don't get that joke, then you've never learned monads before. So I don't know. I'm not merely, this is sort of like weirdly written, obviously, because it's not meant for human consumption. But yeah, if anybody is interested in nerding out with this afterwards, we can definitely sort of dive in and discover the internals of Elm together. So, Raymond, are you semi-satisfied? I'm sorry. We'll talk about it later. All right.
I wonder why does it looping?
Okay, so you're talking about the loop?
Yeah, because you can do it multiple times.
Yeah, yes.
That's not clear for me.
So the loop is sort of like in JavaScript, you also have a loop that runs in the background, right? So you always have this, and it's like an event loop, right? And so Elm also sort of, occupies this space as well. So there's no need, like there was in the Haskell example, of sort of managing your own loop. Just like in JavaScript, Elm sort of inherits from the browser like an event loop that is just listening in on. And Elm sort of takes those events and makes signals out of them. So the way you can envision, once you sort of get signals in your head, you can envision them again as a graph, and they kind of all combine together and make signals, a big signal graph, where you can hook into them using just pure functions. So that's how we handle input. And the last small example I'm going to show is how we handle state. So when you're in a purely functional programming language, you don't have global state. You can't just sort of keep state around, and when you need it, look into it. You have to pass state around with you in a purely functional way. So we have to figure out how we can do that and how we can maintain things. So there's two interesting concepts in here. If we look at main again, right here, we have main, and again, it's a signal of elements. So we know we're going to be working with signals of some type. We're going to be dealing with some sort of input, either from the user or from the world at large. And we have a nice render function, just like we had before, called render number. It takes an int in here and turns that int into an element. So pretty simple. Given some int, it will turn it into an element representing that integer. So no need to sort of worry about that right there. The next thing that we're going to, maybe I should explain what this code will actually do. So what I want to attempt to do here is every time I press the up key, it will increment a number. And when I press the up key again, it increments it and just stays there until I hit the up key again. And it kind of keeps the state of how many times I've pressed up since the refreshing page. So here, we want to have an input of up keys. And we call that a signal of int here. So this will be returning a signal of int here. And we're going to be taking advantage of a function called fold p. Who here is familiar with fold L or reduce or some higher order functions like that? So most people, if you're not familiar with fold or reduce, and Ruby it's called inject for the Rubyists, basically what that does is it takes some function. It takes like a collection of things, you can think of it that way, and it sort of reduces them down to one input, or one value, sorry. So in Ruby, what we use this quite often for is like you have a list of numbers or something, and you want to add them together, you just like inject over it, reduce over it, and it sort of combines them together using a function, the plus function, and adds them together. And enough, that's exactly what it is. So fold p, if we look at its type signature, take some function, and a function where the first argument will be of type, whatever type A, the second argument will be of whatever type B, and then that function should return B, right here. So we'll get to that again just in a second. We start with something of type B, which is our start value, and some input signal here. So our input signal is up key press here, and up key press is, we'll get to that in just a second. We start with the value of 0. So obviously when you load the page, you have never pressed the up key since the page loaded. And then our function that takes a value of type A and type B and returns a B is plus. So plus takes a value of type int and also takes a value of type int, puts them in, adds them together. So what fold P is essentially folding not from the left as in fold L, but folding from the past. So fold P stands for fold from the past. And it's a way of sort of taking signals and sort of remembering their previous state and sort of running them through a function and always keeping the state together. So you sort of loop over it in that way. And it's constantly just repassing the state in. I should mention, by the way, that right here in this function that we have, A will represent the next value as it comes in, and B will represent sort of the sum, the memo, the state that we've collected so far. And in this case, they're both integers.
Question?
Yes.
Is it going forward or backwards in time?
It's going forwards. Actually, as we'll see, doesn't matter. Obviously, when you normally run this program, it will be going forwards in time. But we will do some time traveling. So bear with me. So again, that's up keys, and we also were dealing with this up key press, which we know up key press has to be a signal of type A. We know that type A is int, So up key press has to have type signal event. Hey, and guess what? It does. That's awesome. So we go back to our old friend lift here, which takes some, function that doesn't deal with signals and lifts it up into the signal space. And we get back in our function arrows. So arrows are just this. This is a record type here. No need to worry about what that is. Sort of like JavaScript objects, or they're records in Haskell if you're familiar with Haskell. Kind of like hashes in a way-ish, except they're type safe and they don't grow. They're sort of like objects in object-oriented programming without any functionality, just purely. So anyway, we come in here and we ask ourselves, okay, if in this arrows the y value in that is 1, meaning that means we press the up key. You can read the docs for how that works. Then we're just going to return 1. Otherwise, we return 0, like nothing happened in our world. We don't really care about it. So we'll return 0. And this turns this into a signal event. So it will basically pulsate zeros when you press the keyboard. So if I press the right key, it will send a signal of 0. If I press the left key, it will send a signal of 0. If I press the up key, it will send a signal of 1. And then we kind of fold over that and sort of add these things together. So you're going to do like 0 plus 1 plus 0 plus 0 plus 0 plus 1, and kind of fold over them in that way. So I know this is slightly confusing, but this is how we deal with state. We sort of fold over the signal graph, passing in our previous state, modifying it in some way, and then going on from there. Are there any questions about this? I would assume so.
You said that float p keeps around the past,
Yeah.
so it remembers it.
Not,
Or how does it work? So when it remembers it, I would assume the browser to crash
Yeah.
some way.
So first of all, it doesn't remember it. What it does is it keeps on calling this function, this first function here, this one in the parentheses here. It just keeps on calling it with the next value from the signal that we're talking about and the previous value, so the previous state. So there's only ever 2 values sort of in memory. The sort of state that we have right now and the next value as it comes in. And as soon as we modify that state, we don't modify it, rather we produce a new state, and that will again be passed in this full P. The old values can be getting garbage collected. So there's really no garbage involved here. You're sort of, instead of reaching out into some global state somewhere else like you would in an imperative program, you're always just constantly passing that state back into the function that you're working on. Like that. Great question. Yes, so any other questions before we see this thing and it hopefully works? Yay. All right. Let's go ahead and open this data. And no one can see what I'm actually pressing. I'm pressing the right key right now. I'm pressing the down key. I'm pressing the left key. And now I press the up key. And now I'm pressing the plus key. Here we go. I'm pressing up, and it remembers this thing. So this thing has no global state that it uses. It's just constantly passing the previous state in. So at one point in our execution, let's go ahead and trace that execution real quick. When we have 15 now as sort of the state that we're passing around. When I press the up key again, keyboards will send us a signal of this record of x and y, and we'll pass it into this function. And we'll ask this record of x and y, hey, what is your y value record? And it will say, hey, my y value is equal to 1. And we go, that's great. I'm going to pass along this signal, 1. It comes up here, and now we have a signal that's going to pass 1 through, and we're folding over that. And our state, as we pass it in, so this is our state right here, is 15. So we have 1 and where B is right here, and we have 15 where B is right here, and we add them together, and then we pass 16, the new state, back through the fold P function again, as our new state. So we're never modifying state, we're just creating a new one, throwing away the old state. And you can think of this state as being anything arbitrarily complex. So you can have an integer, or you could have a record. And you will see when I open up my actual game here, that I have a record that represents my game, the game state in itself, all packed into one record, the state of my game. So we'll see that in a second. Does anybody have any more questions before we move on to a big example of Snake, the game that I'm currently building? Any more questions? All right. Yes.
You have also tried to do it with a pipe.
With a pipe, I don't think you could possibly do it with a pipe here because there's no, you can't, pipes, the way pipes work is you would have to have some input and you pipe it into a function where that is the sort of input type for that function, if that makes sense. I'm explaining this really terribly. So you can't sort of pipe signals in because all these functions, all this function right here, for example, doesn't work with signals, it just works with integers, or excuse me, records of x and y. That's all this works with. And our plus function right here doesn't work with signals, it doesn't know about signals at all, it only works with ints, pure ints. So we have to sort of give it to other functions that allow us to use these functions that don't know about signals to then be able to use signals. These are higher order functions that take regular functions and kind of mess with them in certain ways.
Brian, if what we just talked about goes through, you could pipe plus into forgo, but that's...
Oh yes, that is absolutely true. So you could pipe, that's definitely true. I would argue that that's not as readable, but you could do something like this. This would work, because now we're just piping the plus function, which is the first argument to full P in there. And that works. Let's make sure that does work. I'm curious. Nope. So it doesn't work probably because I lied about the way full P works, and I just think of it in terms of Elixir, or not full P. Sorry, the pipe function. But in Elixir, that's how it works. Just to get going. Not in element pairing. So, any more questions about state?
Do we pipe in the up keys? Are you sure it's the first one?
It's probably the last one actually. So if we want to try that real quick and watch me really type terribly because I'm so nervous. And oops, not this one. We want to take this one, move it over here. Oops, and I'm pressing the wrong keys. All my coworkers know how terrible I am at this.
But it's actually an anxiety problem.
It is.
I point that out so that you'll be less anxious.
Oh, thank you. There it is. Yeah, so that's it. It's the last one, sorry. It's the last one.
That's like the curly function.
Yeah, exactly. Which makes more sense. The way they do it in Elixir is with a macro, and there's no macros. So yeah, it works. Yay! So these are all kind of boring, right? We're just like, dealing with simple input and displaying something on the screen. So I implemented halfway because I didn't want to finish it. I wanted to leave it as homework to you to do my work for me and implement Snake. So here is a full Snake game right here. So it's 106 lines. What it does right now, let's just go ahead and show it off to you. So here it is, and here's the, if you'll notice, if I go over it, it's a bug. And the bug is intentional because we're going to fix the bug. That's part of my demo. So if we actually go over, there we go. So we're eating it. So we obviously have a bug where if it sort of doesn't make it directly in the middle, then it won't eat the food, and it doesn't grow. So that's your work, make the snake grow, and keep track of points. You need to do that as well. So yeah, we have this. So we want to take a look at this, and then we'll fix this bug where stuff like that happens. All right. So obviously we have not nearly enough time to go through every single line of this, so you'll sort of have to forgive me for scanning over some of these things. But I really wanted to draw your attention to the way that the program is structured. And if you want to, when we go over these sections of the program, you can think about placing these in different files as well. There's no need to keep them in the same file. I just did it for demonstration convenience. But the first thing you see here is we have our main function, and it's a signal of element, just like we're used to. And down here, I've commented model. So here's some models that we have and functions that work, that sort of helper functions for that model. So we have, a snake, that makes sense. It has an X coordinate that's of type float, a Y coordinate that's of type float. And we also keep around inside of our snake the last arrow that was pressed. Now that I'm thinking about it, a terrible place for this to go. It should go inside of game. But, we can place this thing in here. And there's still, despite all the types helping you out, still, you have to make smart design decisions as well. We have type food here, which is just a record of X and Y coordinates. That makes sense. And here's our game state here. And our game state consists of just the snake, the food, and the score. I don't use score. That's up to you, again, as your homework. But we keep around at all times the state of the game as where is the snake, where's the food? We also have some data here, if you're familiar with ADT, so abstract data, or not abstract data types, sorry, algebraic data types. Here we have a sum type here where we have direction up, down, right, left, last, none, things like that. So we can start, instead of doing what is called stringly typed things where we have passing strings around all the time, we actually have things in type direction. And we know that the direction could either be up, down, right, left. It could be the last one that I pressed, whatever that is, or it could be I didn't press any at all. And we have input, and input is either something of type arrow, which inside of it has a direction, up, down, right, left, last, or done, and then tick. And tick is sort of like our tick that we'll have. And you'll see in a second that we deal actually with frame rates as well. And in that tick is a random number that we use for generating the food's next location. So we won't really get into random number generation, but there is a way to randomly generate numbers in a purely functional way. And if that sounds like craziness, it is. So here we have default snake, which is just placing a snake, in the default position. Same with default food. We have a convenience thing here, snake width, to tell us how wide the snake is. And food to tell us how wide the food is. And here's our default game, which is just a default snake and a default food, and the score is 0. Makes sense. There's nothing here that's really crazy or anything. Should be pretty fairly straightforward to understand. Are there any questions about the model or models that we have here?
Why don't you have a name for the snake?
Because that's your homework. It's your homework. So I don't want to take away the fun from you guys. So the next thing we have is our section called control. So if we're thinking of this in sort of MVC type pattern, we're going to have model, control, and we're also going to have down here a spoiler alert view. So that's how we've separated this game out. Model, view, controller. So nothing really crazy revolutionary here. And control is sort of like it is in typical MVC, sort of putting together the model and the view in one way. We could possibly separate out a fourth section, which is sort of input or signal graph here. So this is setting up our signal graph where we have a signal of games, and it will sort of pipe us, or will like pulsate out new games at us, and we can deal with those games as they come in. And here we have a signal of input. So we're kind of merging together our keyboard arrows and our random number generation here. If you don't fully understand what's going on right now, don't worry about it. This is like we went from simple examples to something fairly complex. So no worries, just know that we're kind of building up these signals where we have a signal of input, we're getting pulsated at us some input, we're also getting a gain kind of pulsated at us, and we can deal with these things using our lift function to work on them using pure functions, which is great. We have here two direction, which takes our old record X and Y that we get from arrows and turns it into an input, something type input. We have a frame rate here, and we have a step game that takes an input and a game and gives us a new game. So this is pretty straightforward, right? We get some input in, we don't get it, and we have some game. This is our previous game. So here we call this like prev game, not fame. Don't type right. All right, so we could call this and then change game in there to prep game as well. And this sort of transforms our game from one game to another game, given some input. Pretty straightforward, pure functions. The nice thing about them is they're quite easy to understand. Given some input, you'll get always the same output every time, which is nice. And here we have a tick game that takes in a tick and a game, and then returns a new game, and stuff like that. And you'll see here, we're going to be playing around with these bugs in a little while. We'll see this program sort of running in real time. This is the non-pure part of Elm, so it isn't quite purely pure. We have things like move food, which takes a random integer here and a food, and it moves it to a new place. And here's a predicate function here, given a snake and some food. What is the food eaten by the snake? So we get back a Boolean, true or false. Was it eaten? Stuff like that. We have a move snake that's just like the move food function above. Does anybody have any questions sort of at the high level about the controller functions here? Anything here? The one thing hopefully that you've noticed is that when you look at the types and the name of the function, like everything should sort of make sense, and you don't have to worry about inside these functions what they're doing, if they're making network calls or something like that. They're not. They are pure functions. So what you see sort of is what you get at the type, at the function signature. you can sort of tell what it's going to do, which is really
Ryan,
nice.
what is the main function again?
Main function up here, it's just a signal of elements.
And
Um,
it calls,
So I don't really want to go over this in full detail, but it's sort of putting together this signal of games that we have, like these games pulsating at us, and also combining that with the window dimensions, so the dimensions of our window, and sort of lifting that up and putting it into a render function. And render does exactly what it does. It takes these things and then creates an element, and that's exactly what we want. We need a signal of elements. So, any questions so far? I'm sort of moving fast on here, but you guys are pretty smart, so. So the next part is the view here, and the view takes care of exactly what we would think it takes care of. Like we have things like render snake, really easy to think about. It takes a snake and it turns it into a form, and forms are things that I believe move around on the canvas. I'm not sure, but you can think of these like things that will be displayed to the screen. So we take the snake model, which is just inside of our game logic, and we turn it into something that the user can see. Pretty easy to understand. Take the snake, make it render. Render food, same thing. Take some food, render. That's fine. Board, take the dimensions of the board. We could type alias this to be dimensions of board instead of tuple event dimen. And take in some two forms. Again, we can type alias this to like snake form and food form, and we get back an element. And the element is exactly what we need to then go ahead and sort of render it on the screen. And here we have the big render function that we talked about. We have the dimensions of our browser window. We have the game that we want to go ahead and render, and then we go ahead and just call the board function. And that sort of does everything that we need it to. And we get an element out, and yeah, we can put it on the screen. Does anybody have any questions about the view in particular here? Cool. All right, so this is like where it gets really exciting. If you weren't convinced already about how these things are really nice to think about, is you can think in terms of pure functions. Like there's not a lot going on here. When you see render food, you just pass in some food, you get back a thing that you can render. Really easy, really straightforward. That's really nice. But purity comes with a lot of great side effects. So, okay. So anyway,
I'm copying that one.
Yeah.
I'm keeping that.
Yeah. Yeah, I'm really impressed with myself. Anyway, so
probably ought to just end it there, Ryan.
yeah. Yeah. So for the astute people in the crowd, you may have noticed this little wrench over here. And this wrench will open up our game inside of debug mode. And the reason, I mentioned earlier that I never opened the console, and this is the reason. You have something like this where you don't need to. So if you see it, this is our debug mode. And you can see that we have our snake and it's being sort of traced with the line, every position that we're in with the snake. We see where it is, where it's been before, like this. So the cool thing about that is, let's see where that actually happens. We have this debug trace here. We give it a string which sort of labels it on the side over here, so we can see. We don't see it over here actually, but this is sort of the snake trail over here you can keep track of. And then it takes a form, returns a form, so it sort of doesn't do anything with it other than side effect and give you a trace on that form. So the nice thing about this is that if you look up here, we have swap here. And what swap is code hot swapping. So because this thing is purely functional, and because no matter what, you always sort of have the signal graph that you've built up, and you have pure functions, and you have no state that can become corrupt when you change code, there's no need to sort of restart the game server or something like that, to kind of go back to your start state to start over. You can literally change things and then go ahead and rerun your program with the same exact input that you had in your previous program. So we're going to, for instance, we have, I think it's move snake. So what happens if we go ahead and do, instead of changing the snake's x coordinate to the previous x coordinate plus the new x, whatever it is, we just go ahead and do 20 every time. What would our game look like now? Not very exciting. But this is exactly what, if we had played the same game with that code, it would have ended up like this. We would have ended up having our snake do this the entire time. Again, not very exciting, so let's go back. Maybe if we do y times 3. Let's see what happens here. If we had played the game with that code instead, we would have ended up with a snake like this. So hopefully you're going, wow, that's pretty cool.
So we are at that point in time where you stopped it, actually.
Yes,
You
we
were
are
seeing-
at that point in the game. Elm, since it has the signal graph, it's there, the runtime has it, it kind of keeps it for you in memory when you're in debug mode, and you sort of have the history of the game right there for you. And you can change code, and it automatically swaps into new source code and shows you, if you had had this code before, this is how your game would have been played.
So it's keeping your signal history in debug
Yes,
mode?
yes, exactly. In debug mode, so it doesn't garbage collect the signal graph. So obviously you wouldn't do this in production because you just have garbage all over the place. But for debugging, this is amazing, right? We can sort of play our game once, and who here has had a bug where, oh, I can reproduce it 1 in 1,000 times, right? And then on that 1,000, oh, I forgot console.log, crap. Oh no, I gotta do it 1,000 more times. That's gone. All of a sudden gone. You never have to worry about that. Do it once, you have it forever. You can change the code in any way you want to and see what will happen.
Can I persist it for the future?
I don't think there is a way, but in theory, yes, you could serialize that somehow, and I don't know how it's represented internally, but there is I would imagine you could sort of serialize it, send it to your friend and say, dude, can't figure this out, can you help me with this? And they can go ahead and help you debug your game. Why not?
But if you have something like physics, like collisions or anything, I mean, what happens?
It's the exact same thing. The exact same. We have here a collision, basically it's not with physics, but we have collision of the snake. Let me go ahead and
But I mean, you show this graph, and on a collision, the thing is destroyed or whatever.
Mm-hmm.
So, what happens? So,
you can sort of think of the way that this happens is you have a signal graph, right? You have it persistent in memory. You change the code, Elm then runs that signal graph through your new code and gets you to your current position in time, basically. So when let me go ahead and try something real quick and show you what happens. So let me just like refresh here, and if ooh, that's weird. Oh, I'm moving the screen around as well. So here we have this, and I've eaten the food a couple of times, right? So let's just stop this. I've eaten the food a couple of times. Let's go ahead and redo this like this. What would happen? Oh, actually I didn't save it the first time, sorry about that. So what happens when I undo it like this? We see that if I had run it with that code, that some of those collisions would have never happened, and my food would have ended up here instead. And the nice thing is, you can sort of slide back and talk like this. So maybe for really...
Is it playing the external inputs, right?
Yes, so it has that signal graph, and it's sort of taken this external input and replaying it over your new code. I don't have internet. There's a really nice, on elmlag.org, there's a really nice demo where they built a little like Mario jumper. So you have Mario, and you jump, and you can play around with it. They have an in-browser editor as well, which is really great. You can change gravity in real time. So you jump up, change gravity, in the middle of the jump, he falls down faster. Then you jump again, and you change gravity to be way less, and he's like flying away. Like, no, come back. So you change gravity to be heavier, he comes back, and then you sort of reverse time and say, oh, what if gravity had been, instead of 9, it would have been 20? What would happen when you see Mario like do what he did before, when he's like, ugh, kind of limping along and stuff like that. You have all the input that you had before, and because you have these pure functions, you can just run sort of the same signal graph through your changed code every time. There's no need to worry about corrupting state. Like this is impossible to do in JavaScript due to the core essence of what JavaScript, for that matter, C++ or C or anything like that, it's impossible to do unless you effectively build an Elm-like thing on top of it.
What about random? What about random number?
Yeah, that's kind of crazy, right? So it sort of produces, if you've ever done like random number generation in Haskell before, you know that it's using an actual random number seed. So really you have like a function that takes a random number generator, like a generator, and you pass it into a function that takes a generator and returns a random number. And so really what this thing is it still has that signal graph, it still has the random number generator there every time, and will pass in the same random number generators. So effectively, it's not really random at all. It's just pseudo-random. I mean, nothing in computing is really actually random. It's pseudo-random, and that means that given that we can pass in the same random number generators to these pure functions that take random number generators and produce numbers, we can pass them in, and we're guaranteed to get the same random number each time, if that makes sense.
Just not the random number, but also a new random
Number generator.
So and then you use, in the next step, you use the next generator, which will...
I was kind of thinking specifically about the case where we basically, so some of the collisions didn't happen. And instead, or so maybe if you made it so that one of the collisions
But think about it.
in the middle somewhere.
There's sort of like a sequence of random number generators that you will have, right? And that will be the same given the same sequence, the same signal graph. So like if I have one collision, then I will go ahead and pass in, if I have one collision, I've passed in a random number generator, gotten out a random number and a new random number generator. But if I got 3, I still would have had that first random number generator I got back, but I'd have 2 more. And if I did 5, then I'd have those first 3. If I had 0, like it's still sort of the future is already there, if that makes sense. There's a really great explanation of the way you create random numbers with purely functional programming and functional programming in Scala, which is a new book out, and I really recommend reading that. It sort of enlightened me in nice ways. Yes?
Is there a way to make that non-deterministic? Like I was playing with an audio program that was in Ruby, and it had the same concept of random numbers where it was pseudo-random and always give you the same sequence. But if you're trying to make something that is actually not deterministic, how do you do that?
I mean, in computers, it's always deterministic.
This specific application, like I want every game play to actually give me a different random.
That's exactly what this is doing.
You just need input sources that are non-deterministic, something like the time, or something like that.
Yeah, exactly. And of course, that's what I think it's the random module in Elm actually gives you. Is sort of if I refresh this page or restart the program with refresh here, the signal graph from the last time you ran will be lost, and I'll have a new signal graph that I'll build up, and it will have a new initial random number generator. So things will be completely different, the same. It's just when given a signal graph, it's always going to be the same random numbers. And of course, though, you don't keep around your signal graphs between gameplay. Every game is a new signal graph.
Can you replay this like recorded stuff just in natural time, like in the same? I mean, you could step through it. Oh, okay.
Oops, sorry. I think there's a way to. I don't know if there is a way actually to sort of say go until the end and play in natural time. I don't think they've implemented that. But there's no reason that you couldn't do that.
Yeah, sure.
So.
Question about the memory consumption of the thing. I mean, because if you're working on a non-trivial game, at some point, a game that it takes 10 minutes of gameplay to get to the point you want to debug.
Yeah.
I don't want to have 10 minutes of in-memory, 10 minutes of state or transitional states in the memory of the browser.
I can't really comment on this exactly because obviously that requires sort of knowledge of how it's implemented internally. Though I have done.
Because it would be interesting, for example, to be able to, if someone was talking about serialization, so to be able to save the state at this point, and start debugging from this point and save.
I wouldn't imagine though that in order to implement this, they would have to keep things in memory that are very big. So as long as you're okay with keeping around, a megabyte of something in memory while you're debugging.
A big game.
But actually, how you explained it, I have the impression that I think you said it right, that it's only keeping around these external inputs.
Yeah.
So if you have a really complex 3D game, I don't care, and you are just using your keyboard, it's not much data.
Yeah.
Where when you play
Exactly. It's only, the signal graph is just external user input and like world input. And the other thing is, this is definitely using persistent data structures. So you have these data structures where you're only basically keeping diffs. When you have a new state of the world, for instance, it's not like you have 600 copies of state. You have the state here and sort of like graphed on your diff and stuff like that around. So if you're not familiar with persistent data structures, that's really an interesting topic. And what's his name, David Nolan, the guy who came up with ActionScript, just recently gave an awesome talk where he talks about how we can implement things like FRP in a very memory and CPU efficient way because of the use of persistent data structures. We're not doing the naive thing, where you would think the naive thing would be, I need a new state, let me just copy the previous thing and modify it a little bit. That's not the way it works. Yeah, that's not the way it works.
There's also another technique that they use in the realm of databases that from one perspective you can see it as a timeline, and as you say, you can recreate every state by just following the timeline. But at a certain point in time you can also do a snapshot. So you just calculate the state of a certain time, and then you use that. From there you can calculate the future. So you could do exactly what you said. So just store the snapshot of the time you can go from there.
So just before we wrap up, we're kind of running out of time. I did want to go ahead and try and fix the bug that we have here, just so everybody can see like how this can help us actually make things much better. So let's go ahead and just restart this. And if we go ahead and there we go. So that, if everybody saw that, we see here. Can everybody see how they actually do collide? Ah, crap. So the debugger obviously needs some work here, but if for those who can't see, the black square and the red square are indeed colliding. So we have a bug here. The food should have been eaten, but it was not. And we can see in our history here, as we go back and forth, like it passes by and then it keeps going. So in the interest of time, I'm going to give away the answer. But one thing we can do, we can see, oh, I see, the food here has these coordinates and the steak here has these coordinates, and I look at the function that I know that is the pure function that's in charge of determining collision. There's an easy one, it's called food is eaten, and it takes a snake and a food and gives us a Boolean back of whether it's eaten. True or false, is it eaten or not? And for the super smart people in the room, probably you have noticed already that we are doing something that we should not be doing. So first here, what we do is we figure out what is the minimum, the X minimum for the snake. Like what is the very bottom of the snake? What is the very left of the snake? What is the very right of the snake? What is the very bottom of the snake? What is the very top of the snake? We sort of get the whole like square around the center point of the snake like this. There's probably much more elegant and better ways to do this, but this is sort of the straightforward way. Let me just ask, do all these conditions hold? Is the food's x coordinate greater than the x-men, but less than the x-max? And is the food's y coordinate greater than the y-man and less than the y-max? So does anybody have any idea what's going wrong here?
Yeah, the food has some extension.
What's that?
The food has some extension as well.
Not exactly what's actually happening, or possibly yes, and I'm just too stupid to recognize that. The one way that it by chance actually fixes it though, is that I'm dividing the snake width by 2, which actually you should be doing, and which is why I originally implemented this bug in the first place. But to fix it, so we don't have to move from this point of the screen, is going to delete the divide by 2 here. And we can see what would happen if that hit. You can see.
Yeah. You probably have to take half the snake width and half the food width.
Well, let's see.
Yeah, that's what I was thinking.
Oh, uh-oh. Where's my food? Where are you going? Oh, I'm always eating. Oh yeah, I am. How did that happen? I don't know. Whoops. That's strange. Oh. I'm not sure. So it could be bugging element is certainly possible. This is pre-1.0 release. So let's see here if we go back and see.
Not actually.
Yeah, exactly. Yeah, this is definitely a bug. That should obviously not happen. But anyway, modulo bugs in the compiler, you sort of get this power where you can control time, and time becomes what Rich Hickey talks about a bunch of times. Time becomes a first-class citizen that you can manipulate on your own. And instead of saying, well, time is something that I'm as the programmer, I'm not powerful enough to control time, we just throw that concept out the window and say, no, time is an input into our program, and we should be able to manipulate it just like any other input into our program. And that opens up a whole new window for debugging possibilities, for expressiveness, and just for ease of understanding of our program. Everything is a pure function. If we give it some input, we know that every time we give it that input, we will get the same output. That is very powerful, makes understanding things way easier, and we don't have to always keep in the back of our head, what is the state of the world right now? If you need to know it, you just look right here. We see it. You can't see it right now, it's my screen. But you can, I didn't print it, but we can print out the state of the game at every point. And instead of having to keep it in our mind, we just print it to the screen and have it there for us. That's quite a nice thing. So that's it for my presentation. Is there any more questions before we end for the evening? Yes. Yes.
Can you just show what you ran to like you have a directory with all these Elm files, and did you literally just run one program and start some?
Yes, it's here, Elm Reactor. So this is in the file that I showed in the browser, right in here.
In the directory.
You just run it, and you run it and go to port 8000 and you have the ability. So on GitHub, by the way, I can't get internet access, but I do have.
Yeah, we have, I guess.
Yeah?
We lost sound.
Yeah, I'm connected, it's just not. But it's fine, I just wanted to show, I do have, called Flappy, where is it? No, it's all gone, sorry. Flappy, if people want to see this on my GitHub page, it's sort of a full game implemented, and it's sort of put out into the 4 parts. So I have my main, my controller, my model, and my view, and you can sort of see how this works as well. And in total, it's around 200 lines of code or something like that, so for a full Flappy Bird game, including the Flappy Bird itself. And if there are no more questions, we can... I did want to ask, by the way, so I'm ending my talk. Thank you very much.